Hey, hello everyone. My name is Sumeet Mahadik, and today we're going to talk about a very interesting topic that is a hybridization. So many students are get confused with this concept that is hybridization. So let's start with a very enthusiastic manner and understand the basic concept of the hybridization. So as you can see on the slide, a hybridization is defined as the concept of mixing of two atomic orbitals. So what is happening here in hybridization? The mixing of orbital is happening. So two orbitals are what is going to happen? They're mixing with each other, okay, with the same energy. But what is the rule? What is the condition? They should have the same energies. Can you see here? These two are orbitals are mixing, but what is the condition? They should have a same energy. So hybridization is nothing but the mixing of the same energy level orbitals which are mixing, right, to give a degenerated new type of orbitals. So why they have to just want to mix it each other? Yes, once they mix, they will form a degenerated. So from instability, they can form a stability. From the instability, they can form the stability. So that's why the hybridization process is very important in the organic chemistry. Okay, so let's move further. So as we know that the hybridization, we know that, right? What is the definition of hybridization we have just done? So let's go further. Yes, the hybridization is nothing but depends on. So the intermixing is best. What is the intermixing? Why the orbitals are mixing of the same energy of mixing? So what is the reason behind that? This is depend on the quantum mechanism. What is the quantum mechanism? In the science, quantum mechanism deals with the matter and the light, right? So it totally depends on the quantum mechanism. You can see here these are the shells. Suppose this is the nucleus, this is the red nucleus. This is the first shell, the blue color shows the first shell, the green color shows the second shell. Okay, I mean say third cell, and this is the fourth cell. So this is a based on the quantum mechanism, the matter and the light phenomena is going to happen. So hybridization is a concept which is based on whom? On the quantum mechanism. Now, the atomic orbitals of the same energy level can only take part in the hybridization that we just have seen in the definition, and both full-filled and half-filled orbitals can also take part in this process. So here is a concept. Which is a concept? What is a half-filled and the fully filled? Fully filled means what? Suppose the duplet and octet is complete. That is called fully filled. Okay, that is called a fully filled. So let's take example over here. See, if I'm talking about the fully filled orbitize. Okay, so suppose I'm taking the p orbital. In the p orbital, you know that three shells are there. So this is the pair, this is the pair, right? This is a fully filled. But when I'm talking about half filled means what? I'm taking a p orbital again. Okay, only one electron is there, one electron is there, one electron. This is a halfly filled. Okay, have you understood that fully filled and halfly filled? What is the thing? Yes. So halfly filled also somewhere stable because in each box the electrons is there. So it's taking care of the stability over here. Okay. So this is fully filled and this is a half filled. So this both things are going to take participate into the mixing, and that leads to the hybridization. Okay, so that leads to what? Hybridization. So let's move to the our same part. Okay, so let's talk about with the help of the diagrams. Okay, so very interesting topic we're going to talk about. So let's start with the PPT again. Okay, so here it is. So the atomic orbitals of the same energy that we understood, both full filled and the halfly filled also we understood. Okay, so take part in the process that provided by they have the equal energy. So fully filled and a halfly filled, if they are having the equal energy, they can intermix each other. Can you see here? This is a p orbital. Okay, and this is a p orbital is here. Okay, are you understanding that things? Okay, let's go further. So now the redistribution of the energy of orbitals of individual atoms to give the orbitals of equivalent energy happens when two atomic orbitals combine to form a hybrid orbital in the molecule. So whenever the two orbitals are combined, there is a happens of redistribution. What is the redistribution? Here, the first electrons are, for example, there is a combination of s orbital and p orbital. So whenever there is a combination of s orbital and p orbital, what is going to happen? They are going to redistribute themselves, right? So we will see in the that 3D diagrams. Just wait for it. So this process is called a hybridization. The new orbitals thus form are known as a hybrid orbital. So whenever there is a combination of the s orbital, p orbital, it leads to formation of the hybridization, right? So that is called the hybridization that we just have understood. Redistribution, the word is very important here because earlier the electrons are moving in the s orbital, and whenever the s orbital combine with the p orbital, now there is a more space, that is p orbital also there, s orbital. So how the electrons are redistributed themselves, that is an important text part in the hybridization process. Okay, so this is our first point, that is what sp hybridization. So when you talk about the sp hybridization, that is a combination of the s orbital and the p orbital. When they combine, they leads to formation of sp orbital. The name itself suggests that, right? So sp hybridization is the observe when one s and one p orbital in the same main shell of the atom mix to form the two new equivalent orbitals. See here, this is the s orbital. Okay, let me show you again. This is the s orbital, this is the p orbital. They're combining again. Now look at the picture. Okay, that GF file, what is moving? They are moving to each other. Okay, so this is the s orbital, this is the p orbital. Whenever they combine, they form some this kind of structure, right? Yes, small outlet and the big outlet is there. So the new orbital form are called sp hybridization orbital. It forms a linear molecule with an angle of 180 degree. What is the angle? 180 degree. So let's see the 3D diagram of this picture. So let me show you these things. Okay, so have you understood this concept? That is very important concept is here. Okay. Yeah. Now can you see there are x-axis, y-axis, and z-axis? Yes. Can you see it? There is x-axis, y-axis, and z-axis. Let me show you that. Okay, so this is x-axis, y-axis. Okay, so these are the axes. You can see. See, I can show you the 3D diagrams. So these are the axes. Okay, these are what axis you can see here. You can see right now, right? So x-axis is here, this is y, and this is z. Now, as we know that this is a combination. Hybridization is what? Combination of the s orbital and the p orbital. So let me show you first this thing. Suppose this is your s orbital, which is a round shape or spherical shape. Okay, these are the things. Plus it get added to the one p orbit, suppose px. So what is the structure is going to happen in this case? Yes, tell me. Yes, exactly, the structure will be somewhat like this. Okay, the dumbbell shape, the combination will be there, right? So here is a dumbbell shape structure will be forming. So let's see that structure. So now, yes, so here is this structure. So whenever the s orbital, okay, I will show you that. So whenever the combination of what, this is a sp hybridization. Okay, this is a sp hybridization. When you talk about the sp, it's a combination of s orbital and the p orbital. We know that s orbital is look like a spherical manner, p orbital is a dumbbell shape manner. So whenever they combine, they leads to form this. So they undergo the hybridization process, and they're going to form this kind of structure. So this is the x-axis, y-axis, and z-axis, the 3D diagram, right? So here it is. So can you see it? Yeah. Now look at from the above portion. So don't you think so? This is a dumbbell shape. Yes, exactly. So it's a combination of that. Okay. See here. Look at very carefully what I'm trying to convey. Yes, exactly. So from the below, from the above, from the sides, it's dumbbell shape. Now, I will tell you one more important thing here. Now, tell me one thing. Suppose you are looking at this front, okay? So, if your y-axis in front of you like this, so now tell me one thing. If the electrons are, if electrons are there, so what's going to happen in this case? See, if the electrons are moving from here to here to here to here to here to here, this kind of electron movement is there. And now this angle, which I'm going to show you, this and this angle is 180 degree. Understand? This is angle is what? 180 degree angle is there. Okay, so this is a linear angle, or we can say linear arrangement, because the angle is what? 180 degrees, showing the proper line, right? So it's a linear arrangement. So SP hybridization always consider as a linear arrangement. So have you understood this concept? Yeah, that is more and more important part over here. Okay, so this is a sp hybridization. Just have a look over here again. Yes, now let's move to the same part portions. Okay, so get start with that. Okay, so we just saw the SP hybridization. Okay, we talk about 180-degree, we talk about the mixing. Okay, so let's move for the further things. Okay, so whatever we just have, we just have a recap. So the 3D diagram, this is the s orbital, this is the p orbital. When they combine, they form this kind of structure. Redistribution happen and it gives rise to linear arrangement having the 180-degree that just we have seen, right? The 3D diagram. So that was the SP hybridization. So that is the first type of the hybridization, that is SP, combination of the one s orbital and one p orbital. Now let's move to the example of the SP hybridization. So all the compounds of the beryllium like the BF2, BH2, BCl2, all related to beryllium. Okay, this compound shows the sp hybridization. And the all compounds of the carbon containing triple bond like C2H2, which undergoes the sp hybridization. So this is an example of the sp hybridization, just we have seen it, right? So structure arrangement while like will be that only. So let's talk about the second point, that is the sp2 hybridization. That is what sp2 hybridization. So how can you say the sp2 hybridization? So here is the sp2 hybridization we can say here. So when you talk about the sp2 hybridization, can you see something here? This is the carbon, this is the carbon, this carbon carbon having a single bond, that is called a pi bond. This orbital, p orbital, and the p orbital of the second carbon having the pi bond, this having the pi bond. So don't you think so there is a double bond will be there? Yes, so 1 1 1. So there will be the bonding will be there. So sp2 hybridization is observed when a s, one s orbital and two p orbital. So there is a triple bond, actually we can say, right? What is the carbon valency? 4. So out of that, 1, 2, 3 goes here. So that is a double bond actually. Pi bond is what double bond. So one s orbital and the two p orbitals of the same shell of an atom mixed to form the three equivalent orbitals. The new orbitals form are called the sp2 hybridization. What is sp2? 1s and 2p orbitals, when they combine, it gives rise to the sp2 hybridization. Okay. So one sigma bond and two pi bond will be there. See, here is a single bond. Here is a double bond will be there. So how they actually form? So 2s orbital, which orbital? 2s orbital having the one electron, 2px and 2py. So this is the px orbital, this is the py orbital. See, they're having the same energy. That's why they combine. So whenever they combine, it will give rise to this kind of structure. That is the sp2 hybrid orbitals. So sp2 hybridization, three single bonds will be there. That is a sigma bond. So 2s, one electron, 2px, one electron, py, one electron, pz, one electron. But out of that, only 2s, 2px, and 2py are combining because they are having the same energy. 2px is not going to happen here over here. Okay, so this is going to form a pi bond. Okay, so pure pz, this is a sp2 hybridization, sp2 hybridization, sp2 hybridization. Okay, they are going to undergo hybridization, but that pz is not going to have the same energy. That's why it's going to form a pure pi bond. So that pure pz is showing with a black color. So have you understood that point? Yes. So sp2 hybridization is also called the trigonal hybridization. Why it's called trigonal? Because 1 2 3 4 trigonal cycles. Okay, so it shows the trigonal geometry. So it involves the mixing of the one s orbital and two p orbitals of equal energy give a new hybrid orbital known as the sp2 hybridization. So it gives you rise to new orbital. Now, a mixing of the s and p orbital form in the trigonal symmetry, just we have seen it. Okay, all the three hybrid orbitals remain in the one plane and make an angle of 120 angle, that is 120 degree with another. So each of the hybrid orbitals has 33.33% s character and 66.6% p character. Why so? So in that sp, there was 50%, 50% only s and p. One and one was there. Here 2p, that's why 66.66%, and here 33.33% are there. So have you understood this kind of things? Okay, so let's move further. So sp2 hybridization, can you see here? One s orbital, two p orbitals, when combined, undergo formation of this. So the molecule in which the central atom is a link to the three atoms, and the sp2 hybridizers have a trigonal planar shape. So we have understood that, right? So now let's see the example of this. Okay, what are the example? ethylene. See, BF3 and BH3 also show the same thing. Like 1s of the boring has a fulfilled electron, 2s fulfilled electron. The p orbital is not that much fulfilled. So 2s having these two electron will jump to the p orbital. See here, okay? They have a same energy, so they will contribute to the sp2 hybridization. Let's talk about the ethylene structure, that is C2H4. Okay, so let's start with ethylene structure. Yeah, this is the ethylene structure over here. Okay, so there is a double bond. Can you see this structure? Okay, this white I will show you from here. This white bonds are showing the hydrogen and this black bond showing the carbon. Okay, so let's slice it. Okay, so this is a hydrogen. This is what? A hydrogen. Okay, this is a one carbon molecule. This is the second carbon molecule. Okay, so if this and this is the carbon molecule we just have seen, right? And this bond is a bond with the hydrogen, this bond with the hydrogen, this bond with the hydrogen, and these two bonds are with what? Carbon carbon double bond. So we have to study this structure. Okay, let's slice it. Suppose I'm going to slice this hydrogen. Okay, we'll show you that. Okay, now look at this structure. This is a carbon carbon double bond will be there. Yes, carbon carbon double bond will be there. So this is the ethene structure having a carbon carbon double bond. Okay, have you understood that? Now, whenever the hydrogen popped up, like see here, the hydrogen forming the bond with this. So what's going to happen? This hydrogen forming a single bond. There is no issue. Okay. So if you slice this again, see, I will show you something. I don't want this hydrogen bond to show you, because what's going to happen in this case? This carbon carbon forming the double bond that we just have understood, right? And now, whenever it's going to form a bond, whenever it's going to bond, what's going to happen in this case? This hydrogen molecule. See, this is one hydrogen molecule. It's going to form bond with the carbon. This is the another hydrogen carbon, sorry, hydrogen molecule going to form with this carbon. So the two hydrogen, one carbon, because carbon valence is 4, so it's going to form. Then next hydrogen is going to form bond with this. Next hydrogen going to form bond with this. Okay, so have you understood this? How the ethene molecule, and this is going to show the sp2. And one more thing, the angle between this is 120. Okay, so it's showing the 120 degree. And why it's going to trigonal? Why trigonal? This is 1, 2, 3, and 4. So it's going to show a trigonal geometry. Okay, it's going to show us a trigonal geometry. So what is the angle between that? 120. What is the angle between the SP? 180. That's a linear arrangement. This is not a linear arrangement. This is a trigonal geometry or trigonal shape. Okay, so that what we have just studied here. Okay, so this is the ethene structure. Just have a look over here. Okay, so this is the ethene structure that we have understood. Okay, so we talk about the sp hybridization. Now we are talking about the sp2 hybridization. Okay, so I hope the concept is clear to you. So let's go back to the point. Yes, so I hope the point is clear. We talk about the sp hybridization and sp2 hybridization. Okay, so we start with the hybridization. We have the definition that is mixing of orbital. So we talk about the sp, where the combination of the s and p orbital that we have seen. Then sp2, we have a one s orbital and two p orbitals are there. So we done with the topic name as a hybridization with the two types, that is sp and sp2. So thank you for paying attention.